Hello everyone, my name is Khanh. I'm a PhD student at the Arctic University of Norway, and today I'm pleased to present my paper at the OMAE Conference 2022. The title of my paper is Life Cycle Cost Analysis on a Marine Engine Innovation for Retrofit, a Comparative Study. The other co-authors of this paper are Professor Lokukaluge Perera, Professor Jan Emblemsvåg, and Professor Halvor Schøyen. And this paper is part of the SEATECH project, which has been funded by the EU's Horizon 2020 Research and Innovation Program. This is the paper outline I'm planning to cover. I will start off by giving you the background of this study, followed by research objective, the methodology, and then I will focus on the results we got so far. Finally, I will wrap up with the conclusion. Background. The shipping industry is striving to reduce its environmental footprint and to comply with stricter regulation and ambitious targets regarding air emissions from ships. So with that in mind, the EU-funded SEATECH consortium is developing two innovative technologies. The first one is a biomimetic dynamic wing mounted at the ship bow. The second technology is the dual-fuel engine innovation, based on the idea of achieving ultra-high energy conversion efficiency by precisely controlling the combustion process. So with the high efficiency and the use of a clean fuel, the LNG, running this engine will result in extremely low exhaust gas emissions. So the dual-fuel engine will be the focus of this study. If this engine is introduced into the market, its total life cycle cost is attracting attention from ship owners. Research objective. Throughout this presentation, I will refer to the dual-fuel engine as the SEATECH engine. The research objective of this study is to conduct the life cycle cost analysis on the SEATECH engine compared to that of a conventional diesel engine. Data needed are collected from many sources for doing this analysis, and the expected outcome would be an economic key performance indicator KPI with respect to the total cost performance and the retrofitting investment that can be used as a decision support tool for ship owner at the early stage of the decision making process when they decide to make any retrofitting investment in their fleet. Methodology. In short, we build the life cycle costing model from an engineering build-up approach, where we devise a cost breakdown structure for the engine, and then we sum up on the costs associated with the life phase of the engine, from construction, operation, maintenance, and end of life. The net present cost can be obtained as the summation of the present values of the costs that are considered, as you can see in this equation. Results. Regarding the construction cost, we got the information from Vasila in terms of the main components and system of a conventional diesel engine, as you can see in this table, along with the cost range associated with that. So we got the construction cost in average for this diesel engine, and this is the cost for the SEATECH engine. So the construction cost of the SEATECH engine is a little bit higher than that of the diesel engine. With regard to the operation cost, in this study, this is the fuel cost. We assume other non-fuel operating costs are the same for the two engines. So we need to find the lubricant oil consumption, fuel oil consumption based on this equation. And based on this operational profile of a case ship using the diesel engine. So the specific fuel oil consumption and specific lubricant oil consumption can be obtained by doing interpolation and extrapolation between the actual values and the reference values, as you can see in this table. So this is the figure representing the relationship curve between the engine load and the specific fuel oil consumption. For the operation cost of the SEATECH engine, the engine is running on the ultra low sulfur diesel in diesel mode, LNG in gas mode. We assume this maneuvering is the diesel mode, and these two, engine mode 1 and engine mode 2, are the gas mode. For the fuel oil consumption in diesel mode and lubricant oil consumption, it is similar to what we did for the diesel engine. For the fuel gas consumption, we use this equation for doing the calculation, and this table provides several information regarding reference values for doing interpolation and extrapolation. This figure illustrates the relationship curve of specific fuel oil consumption and engine load in the diesel mode. And this figure represents the relationship curves of the specific gas consumption, specific pilot fuel consumption, and engine load in the gas mode. We did the scenario analysis because we realized that the operation costs are down to the fuel price. So in this first scenario, the MGO price, which is the orange one, is lower than the LNG price, which is the blue one. So the annual cost of the SEATECH engine is lower than that of the diesel engine. So this is considered as the normal case. But lately we can see that there has been a peak in terms of the gas price. So in the scenario 2, the price of LNG is higher than the price of the MGO. So this makes the SEATECH engine has higher annual operation cost than the diesel engine, as you can see. In terms of the maintenance cost, there are two cost components, the labor cost and the part replacement cost. We managed to obtain the maintenance schedule from Vasila, and we did also several interviews with chief engineers and engine officers on board to ask them the actual hour consumption for doing these maintenance activities. Several contributing factors for this calculation are the service interval, the fuel type, the average load, and the running hours of the engine. So we came up with the maintenance costs, as you can see here, for these two engines. So in order to obtain the N applied value of the engine, we need information in terms of the weight of the engine, the material weight ratio to the engine weight, and also the benefits of the recycling. So in the end, we came up with these N applied values for these two engines. We computed on the cost while considering the effects of the time value of money with a discount rate of 2.5%. So we got the results of the net present cost NPC. In the first scenario, which is the normal scenario, we see the NPC of the SEATECH engine is lower than that of the diesel engine. So the SEATECH engine is the cost-effective solution. But in scenario 2, which is we can say an extreme scenario, it is a different story where the SEATECH engine is not cost effective because it has a higher NPC than the diesel engine. However, there is a clear environmental benefit of running the SEATECH engine, regardless of fuel price scenarios. We use this equation to calculate the annual amount of CO2 emission generated from each engine, and then we compare the life cycle CO2 emission emitted from these engines. So opting for the SEATECH engine will result in 33% of CO2 reduction. Conclusion. So there are two main key takeaways. The first one is the net present cost of the SEATECH engine is lower than that of the diesel engine, except for the high fuel price differential scenario, meaning that the results are sensitive to the fuel cost. The second one is a CO2 reduction of 33% can be achieved when opting for the SEATECH engine. Thank you.